Okay, welcome to the third video. In this video, we will show you how to add hyperparameter tuning into the notebook. In the previous section, I showed you how to add some basic login into the notebook, but in this case, I wanted to show you an example that is a bit more complicated. And also I will show you how to explore the results of the hyperparameter search using the MLflow UI. Finally, we will discuss, what is the best model based on the results that we got. Towards the end, I will also show you auto login, which is a very interesting feature from MLflow, which will enable to do some login, but with using much lesser number of lines of code. Let's get started. So here we have the examples I showed you in the previous section. Here you can see that we had this lasso model, and we were just playing with the hyperparameter alpha. Actually, I can try, running another experiment run with a different value for alpha, right? If we go to the MLflow UI, we will see that, this new run appears here. And of course, we can compare these two runs. In this case, we have different visualizations that we can use to compare these two runs, but using only, two runs is not very useful, right? We cannot say much about this model. So instead, I wanted to show you an example using another model, which is XGBoost. We'll try to optimize the hyperparameters of this model using hyperopt, and then we will log all this information into MLflow. So for this, I have prepared some code here. Let me just copy this. Okay, this is imports, and let me explain what we are doing here. So of course, we are importing XGBoost first, and then we will import in some methods from hyperopt. So this is the method that we will use to minimize the object function, right? So basically, hyperopt is a library that uses some Bayesian methods to try to find the best set of hyperparameters. In terms of hyperopts, your model will be just a function that takes in some parameters, and then it outputs some value, right? And this method fmin basically will try to minimize that output. For that, we need to pass also a set of values that the library will use to try to find the minimum output. The algorithm that is used to control this logic is basically called TPE. Then HP is basically a library that contains a bunch of different methods to define the search space. So what are the ranges for each hyperparameter that we will use? This status OK is basically a signal that we will send at the end of each run to tell hyperopt that the objective function has run successfully. And then this trials object will keep track of the information from each run. This method is also, we will use it to define a range of type integer. The first thing that we need to define is the objective function. Let me just take this out. In this case, you can see that I just started this objective function by reading these parameters, right? These are the set of parameters, hyperparameters of XGBoost for this specific run. These parameters will be logged to MLflow, but we also pass the parameters to the XGBoost model to generate this booster object. We are training XGBoost using these parameters on the training data. I will use the validation set to control this, the optimization algorithm from XGBoost. XGBoost will try to minimize the error on this validation set. We will set a maximum of 1,000 iterations of the booster. If there are 50 or more iterations without an improvement on the validation error, then the optimization of XGBoost will stop. Once the model is trained, we will make predictions on the validation set just to calculate the target for the validation set. And here we will calculate the root mean square error also on the validation set, which is basically what we will log at the end of the run. And then we just return the loss. So hyperopt is able to optimize this metric, and the status OK, which I mentioned before, that is just a signal for hyperopt to know that the optimization was successful. Here, we need to define next the search space. When we say search space, we mean the ranges in which I want hyperopt to explore the hyperparameters. For example, this is one of the hyperparameters of XGBoost that is called max depth, and it controls the depth of the trees. So for this, we are sampling using this method QUniform from 4 to 100 levels. This is the ranges in which we want to explore these parameters. But this method, it returns a real number, so like a float. And we want to convert this into an int because this parameter is actually an integer. Then we will define the learning rate using a log uniform space from -3 to 0. In this case, I think that it's useful to check the documentation from hyperopt space, define space. So this one, because it's very complete and it will allow you to understand, what we are trying to do. So before I show you QUniform, which takes a low, high, and Q, and basically it returns a value that is like the rounding of sampling using a uniform distribution between low and high and dividing this by Q, and then it multiplies this by Q to get the final result. In the case of a log uniform, it's basically drawing values that follow this distribution, the exponential of the uniform distribution between low and high. So here you can put the limit. But in practical terms, it means that the variable will be constrained to this interval, exponential of low and exponential of high. So coming back to this example, if we define log uniform -3, 0, it means that the interval in which we will explore this value is exponential of -3 and exponential of 0, right? So we are basically trying values which is around 0.01 and 1, right? X3. Okay, sorry, -3. From 0.05. Okay. So here, yes, the range will be basically from 0.05 to 1. So we are trying some learning rates that are a bit high, but at the beginning, it makes sense with the XGBoost to try some values that are a bit high, and later we can, try with lower values. And then the same with, alpha, lambda, mean child weight, and so on. This is the objective that we will use, regression objective, because this is a regression problem, right? And then once we define it here, the objective function, we define it the search space. We just need to pass all this information to the fmin method, which will try to optimize this objective function by minimizing the output. Then we pass the objective function, the search space, and then here, this is the algorithm that we will use to run the optimization, which I mentioned before, TPE. And the number of iterations is set to 50. I think that this should be enough for now. And we need to pass these objective trials because this is where all the information about each run will be stored. So if I just run this, so I just imported the XGBoost and hyperopt, I defined the objective function, I defined the space, and then I run the optimization. And again, I have another error. Train is not defined. Okay, so yes, what's the problem here? So here you can see that we have train and valid. If you want to train the model using XGBoost, you need to pass specific data type here for the training data set. Let's create it now here. So train will be XGBoost, the matrix, and we need to pass the data. The label will be Y train, okay? And same thing for the validation data. XGBoost, the matrix. This is xval, I think, and the label will be contained in yval. Okay, it worked. So now let's try it again. Okay, so now it's running. You can see here XGBoost started optimizing the validation root mean square error, started on 16, and after a few iterations, we already have better results than the ones we achieved with logistic regression. If we go to MLflow, to the UI, we will find here that there are new runs. Okay, and New York City department here, taxi experiment. I'm gonna sort this by time. So 35 seconds ago, we started the experiment and we are logging all this information. So this is the first run, right? Basically here you can take a look at the values that the optimization algorithm has selected for each of the hyperparameters. So for example, for the learning rate, right? We gave a range between 0.05 and 1, and the value that was selected was 0.25, more or less that. In the case of the max depth, 54 was selected, and so on. And then there is some tags here. Yes, so the model is XGBoost. Let's go back here to see. So yes, this is moving forward. This is still optimizing the first model, but if you wait more seconds or minutes, you will see that this model finally is trained, and then it will move on to the next combination of hyperparameters. So this is the iteration 1 out of 50. And then we will come back in a while to see the results. Okay, so instead of waiting until this finishes, because it's gonna take almost 2 hours, right, to finish, actually we can explore here the results because I have already run this before. So first I'm gonna filter the runs based on the name of the algorithm. So let's see here, there is a tag, this model XGBoost, and then tags model XGBoost. If we search, then here we can see all the results we got with this tag XGBoost. That's why it's important sometimes to add tags, because you can easily filter the results that you are interested in. Then I'm gonna select all of them and I'm gonna compare them. So yes, if you do that, the first visualization that you will see is this parallel coordinates plot, which is a nice visualization when you have a lot of hyperparameters and you want to visualize them. I'm gonna add root mean square error here, which is the metric we are trying to optimize. So you can see that the hyperparameter optimization algorithm has tried many different values for each of the hyperparameters. Depending on those values, we achieve different values in the error, right? Different errors. Root mean square error went from 6.3 up to 6.68, which is, in all these cases, we get better than the baseline model. But still, we may be interested in understanding which combination of parameters are achieving the best results. So for that, you can use the highlighting tool. So here, for example, if you click on this edge on the right, you can select the lower values of the metric. You can easily spot that actually lower values of this metric mean child weight are correlated with lower values of root mean square error. In the case of max depth, it is not that clear, right? Because sometimes you can have 6 and sometimes you can have 80, and still you will have a low value for this metric. And then in the case of learning rate, it's also clear that we may want to continue exploring lower values of these hyperparameters. You can play with this also, like trying to see what are the values that performs the worst. In this case, it's difficult to say. Basically, bad combinations of parameters, it seems to be related to high values of root mean square error, but there is no clear rule here. Another plot that you can take a look is a scatter plot. So in the case of a scatter plot, for example, here I'm plotting the root mean square error on the x-axis versus the learning rate on the y-axis. And here you can see that the hyperparameter optimization algorithm was trying many different values for the learning rate. There is no clear pattern, but it seems that for some reason this area, right, was explored more by the algorithm. You can see that actually the root mean square error was lower sometimes when the learning rate was low. In the case of max depth, I think that there is no clear pattern either. Actually, in this case, it's more confusing. I'm not sure if this is actually affecting that much the metric, but if you see mean child weight, there is a clear pattern here, right? So in this case, except by this point that maybe, you know, the problem is that the other hyperparameters were not well configured, it seems that the lower values of these hyperparameters are correlated to lower values of the error metric, root mean square error. Finally, you have contour plot. First of all, let me just reverse the color because this is an error metric, so we want to minimize it. In this case, you can explore multiple, actually 2 hyperparameters at once, right? The scatter plot only allows you to visualize one of them, but in this case, you can see 2 of them. The contour of this maybe elevation that is represented with different colors is basically the value of the error metric. By looking at this plot, let me just select mean child weight. So you can see this is the same information we saw before, right? It's just a confirmation, but it seems that lower values of mean child weight are typically correlated with lower values of the error metric. By looking at this visualization, you can also decide to explore further this area, right? So not only lower values of mean child weight, but also lower values of the learning rate. There seems to be like here a nice area in which most of the models trained with these values are achieving very good performance. So this is it for now. Let's see now what's next. Okay, so we should select the best model based on this. There is no rule for this. I think that it will depend on what you're looking for, and actually you should look at other aspects, right? But in general, what you can do in order to select the best one is to come here, right? IRA filter XGBoost because I know that it's performing best, and I can just sort the results by the metric, right? So if I do that, I can see that this model achieved very good performance. Actually, it was the best one. And here I get access to the parameters. This is a set of parameters that you need to use to train this model and the value of the metric. So we can decide maybe that this model is the best one, but I will also suggest that you take a look at what is the training time, maybe also evaluate, what is the size of this model, because I don't know, in this case, it doesn't seem to be a big model. The max depth is 17, but still it could be that sometimes the models that have a lower value for the metric are actually huge model, and maybe you want to go with another model that is maybe doesn't achieve the lowest error, but it has a lower complexity, right? And then it can run faster and so on. But in this case, let's say that we will go with this one because I think that it's working well. I want to show you one more functionality from MLflow, the hyperparameter tuning process that we started. I already show you the results, so I'm gonna stop this for now, okay? And so let's say now that we want to train the model using the parameters that we obtain. I'm gonna just copy and paste those parameters. This is the model, right? And I'm gonna just copy and paste these ones here. And let's also take the model from here. This is the training. Actually, we just need this. So here we will train the model. Params, plus a dictionary with these values. I think that there is a more efficient way of doing this. Okay. So now we have the best parameters that we found using the hyperopt. And then I'm gonna train the model one more time using these parameters, but I want to save the model and I want to log the training into MLflow. So one way would be to just add here, right? The with statement and start the run, MLflow, start run. And then here I will need to add, I don't know, some tags like MLflow, set tag, and so on, right? Like then the parameters, so log params, and so on. But there is another way of doing this, and it works only with certain frameworks that you can explore actually here. If you go to MLflow, autolog, so autologging. So if you are training a model using one of these frameworks, namely scikit-learn, TensorFlow, and Keras, Gluon, XGBoost, LikeGBN, StatsModels, Spark, FastAI, or PyTorch, then you can use the autolog functionality, which basically will allow you to log a lot of information about your experiment. You may need to log extra stuff on your own, but still this basically will allow you to speed up the process. With just one line of code, you can log a lot of information. But let me just show you that. In order to enable autolog, you just need to do MLflow.xgboost in this case, because I'm using XGBoost, and autolog. Okay, let's just run this. Okay, you can see that the training has started. We already know that this model took 47 seconds to train, so we should make sure that it takes the same time. And if we come here to the UI and sort this by time, so we can see there is a new entry that was started 19 seconds before, and you can see that there are way more parameters. You know, all this was logged automatically by MLflow. So for example, the number of early stopping rounds, the learning rate, and the metrics. So here you can see the evolution of the validation root mean square error across time. And let's wait a bit more to see the rest of the metrics. So this, yes, here you can see it didn't finish yet, but soon it should finish. Let's wait a little bit more. We set the maximum of 1000 iterations, so it should finish before 1000.
Is there no early
Yeah.
stop?
Yes, there is early stopping, but it seems that this is still minimizing it. So maybe it should stop before 1000 or at 1000. Okay. Come on. Okay, I guess that it is logging the information here. Okay, so the training has finished here after 2 minutes and 25 seconds. I assume actually this is not only the training, but also MLflow was logging information. So let me show you what we have here. Again, we have the hyperparameters of the model. Actually, a more complete set of parameters were logged here. We have 3 different metrics here, right? And then the root mean square error for validation is the one I showed you before, but it also saved what was the best iteration for the model and when we stopped the optimization. And this is also interesting. It's saving some visualization about the feature importance of the model. It's not rendering very nicely. Doesn't matter, but yes, it saves information about the importance of the features. And also here it's saving the model as an MLflow model. So what it means is basically that you have the model itself, this model.hgb, and also here MLflow is keeping track of the dependencies. So if you want to launch this model to run it, you will need to install these dependencies. Basically, MLflow is looking at the code environment in order to keep track of the version of the libraries. It also saves the same information, but as a code environment, and you can see here the version of Python that I used to train the model. And also you have pip and the libraries that we were running. Finally, this ML model file is something from MLflow, and basically it tells you some relevant information to run this model. And you can run it as a Python function or as an XGBoost model. So depending where you are trying to load this model to make predictions, you may want to use one of these 2 flavors, right? If you click here, actually you can see examples from MLflow about how to load the model. This is the end of the 3rd video. I hope you enjoyed. We briefly show you how to tune the hyperparameters of an XGBoost model using hyperopt and how to explore these results using MLflow. We also discussed briefly how to select the best model using MLflow and how to identify maybe some areas in the hyperparameter space that can be further explored. In the next section, I'm going to show you how to log models with MLflow, how to save them, and then how to retrieve those models to make predictions. In this section, I show you that autolog can be useful if you want to very quickly have a tracking of your experiments, and it also saves information like the model itself. But I will show you how to do this manually, right, using the MLflow SDK, and also how to control the behavior of how you want the model to be saved and how you want it to be retrieved.